Today, we're diving into one of the most mind-bending objects in the entire universe, the black hole. We're going to break down what they really are, where they come from, and how on earth do we even see something that's literally invisible?
So, let's start with a wild idea that sounds like it's straight out of science fiction. Could a prison exist that's so powerful, not even light, the fastest thing in the universe, can escape? I mean, think about that. You'd need a gravitational pull so strong that the escape velocity, the speed you need to break free, is faster than light itself. What does that even mean?
Well, the answer isn't a hole at all. It's much, much weirder. What we're really talking about is an extreme warping of space and time. You have to imagine space-time as the very fabric of our universe. And a black hole is a spot where that fabric has been stretched and twisted so incredibly much by a huge concentration of mass that every single path, no matter which way you turn, just leads deeper inside. It's where gravity becomes the ultimate dead end.
All right, to really wrap our heads around this, here's how we're going to tackle it. We'll start with what a black hole is. Then we'll look at how these behemoths are born. After that, we'll talk about the infamous point of no return, see how they literally bend reality, and finally, figure out how we've actually managed to glimpse into the abyss.
Okay, first things first. What are we really talking about here? The concept has actually been around for centuries, but it was Einstein's theory of general relativity that finally gave us the tools to understand what was going on.
So let's get one thing straight. A black hole is not some kind of cosmic vacuum cleaner just sucking up everything in sight. It's actually a region of space where a massive amount of matter has been squished into an unbelievably tiny volume. And it's that incredible density that warps space-time so severely, creating what we call a black hole.
Which, of course, leads to the next big question: how does something so totally extreme even get made? Well, the most common way involves the spectacular death of a truly enormous star.
And this really breaks down that whole cosmic battle. You see, a star spends its life in a constant tug of war. The outward explosion from nuclear fusion is pushing out, while its own massive gravity is crushing in. But for a star that's, say, 20 times bigger than our sun, once it burns through its fuel, gravity wins, and it wins in a big way. The whole thing collapses catastrophically. This can trigger a massive supernova explosion, blasting the star's outer layers into space, while the core just keeps collapsing and collapsing until it becomes a black hole.
Now, every prison needs a wall, right? A boundary you just can't cross. For a black hole, that wall isn't made of rock or steel. It's made of warped space-time itself, and it's called the event horizon.
The craziest thing is, if you were falling into a black hole, you wouldn't feel a thing as you crossed the event horizon. There's no bump, no sign, nothing. But in that instant, you've crossed the point of no return. Every possible path now leads to the center. For someone watching you from a safe distance, though, it would be a totally different story. Because of time dilation, they'd see you slow down, get redder and dimmer, and look like you're frozen in time right at the edge, fading away forever without ever seeming to fall in.
And this formula, the Schwarzschild radius, it really puts the sheer density of these things into perspective. It tells you how small you'd have to crush an object to turn it into a black hole. For instance, if you could somehow take planet Earth and squeeze it down, it would have to be the size of a sugar cube to become a black hole. Our sun? You'd have to compress it into a ball just 3 kilometers across. It's just mind-boggling.
All of this really comes back to Einstein's big idea. He taught us that gravity isn't some invisible force pulling things. No, it's the result of mass and energy literally bending and curving the geometry of space-time. Yeah, this is the classic analogy, and for good reason. Think of that rubber sheet. A planet like Earth makes a little dent, a star makes a deeper one, and other objects, like marbles, just roll along those curves. That's what we see as orbits. But a black hole? A black hole doesn't just make a dent. It punches a hole so deep it looks like a bottomless well.
And this visualization really captures that idea. It's not just that things fall into a black hole. It's that space-time itself is flowing into it, like water down a drain. And anything caught in that flow, even light, gets carried along with it. That's why escape is impossible. You can't outrun the fabric of reality itself.
And this bending of reality has effects we can actually see. When light from a distant star passes near a black hole, its path gets bent. We call this gravitational lensing. And for us, looking from Earth, it can make that star look like it's in multiple places at once, or smear its light into strange arcs and rings. It's actually one of the main ways we find these massive, invisible objects.
Okay, so if black holes are truly black, how in the world do we study them? And what do our laws of physics say is happening at their very core?
This is where things get really, really weird. So, according to general relativity, right at the center of a black hole is something called a singularity. It's a point with zero volume and infinite density. And right there are two great theories of physics. Einstein's theory of gravity for big stuff and quantum mechanics for tiny stuff. They just stop working together. They break. Figuring out a theory of quantum gravity that can describe a singularity is pretty much the holy grail of modern physics.
So since they trap all light, you can't take a picture of a black hole. But what you can do is take a picture of its shadow. And in 2019, an incredible project called the Event Horizon Telescope, which is basically a network of telescopes all around the world working together, did exactly that. They did the impossible. And here it is. This is that groundbreaking image. It's the supermassive black hole in the center of the M87 galaxy. Now, that dark spot isn't the black hole itself, it's the shadow it casts on the bright material behind it. And that glowing ring? That's gas and dust heated to billions of degrees, swirling around the edge at nearly the speed of light right before it falls in. The fact that one side is brighter is proof of that insane speed, and it confirmed Einstein's predictions perfectly.
And these things aren't just rare curiosities. We now believe these supermassive black holes are at the heart of almost every big galaxy. Right in the center of our own Milky Way, astronomers have watched stars whipping around an invisible point at incredible speeds. The only explanation is a black hole. We call it Sagittarius A star, and it weighs about 4.3 million times as much as our Sun.
And that really gets to the core of it. Black holes might seem like cosmic monsters, but they're not breaking the rules of physics. They are the rules of physics taken to their absolute extreme. They're what happens when gravity is left completely unchecked.
So in the end, black holes are a huge part of the cosmic story. They're born from the death of stars, and their gravity helps shape the galaxies we see today. They are nature's ultimate laboratory, pushing our understanding to the very edge and revealing just how connected mass, space, and time really are.
And that kind of leaves us with one last big question. We predicted black holes with math long before we ever saw one. So it really makes you wonder, what else are the laws of gravity telling us about the universe that we just haven't figured out how to see yet? What other secrets are hiding in plain sight?